There is a place in the solar system where the sun looks like a bright star, not a disk, not the overwhelming light source that fills a summer sky or warms the surface of a road until the air above it shimmers, just a point. Brilliant, yes, far brighter than any other star in that sky, but a point nonetheless. Something you could cover with your thumbnail if you held it up at arm's length. From Uranus, the sun is roughly 400 times dimmer than it appears from Earth. From Neptune, nearly 900 times dimmer. The light that reaches those worlds is cold in a way that the word cold does not quite capture. It illuminates without warming. It marks the difference between day and night, without changing the temperature in any meaningful way. The surfaces and upper atmospheres of those worlds are so far from the source of the solar system's heat that the sun's warmth barely registers against the temperatures those places naturally hold. Both worlds sit at temperatures near or below -200 degrees Celsius. The wind on Neptune moves faster than the speed of sound on Earth. And yet, for all of that, for all the cold and the distance and the speed of the storms, these are not strange or alien places in the way that science fiction imagined the outer planets. They are not barren rock fields or frozen wastelands. They are fluid, layered, magnetically complex worlds with ring systems and moon families and interiors that almost certainly contain more water than exists anywhere else in the solar system combined. They are among the most common type of planet in the galaxy. And we have visited each of them exactly once. One spacecraft, one flyby, a few hours of close observation for each, gathered over a few days in the late 1980s, and then nothing. Voyager 2 passed Uranus in January of 1986. It passed Neptune in August of 1989. The images and data it collected during those brief windows remain, nearly 4 decades later, the best close observations humanity has ever made of either world. No orbiter has ever circled Uranus. No orbiter has ever circled Neptune. No lander has ever attempted their moons. No probe has ever descended into their atmospheres to measure what lies below the cloud tops. The questions Voyager 2 raised in those 2 brief encounters have been sitting open ever since, accumulating alongside new questions raised by telescopes that can see these worlds only as small, blurred disks from a distance of billions of kilometers. Tonight, we are going to spend time with those 2 worlds, not rushing through them, not treating them as footnotes between Saturn and the edge of the solar system, just looking carefully, in the way that things only reveal themselves when you are patient enough to stay. The story of how we found these 2 worlds is in some ways a story about mathematics arriving before observation. Mercury, Venus, Mars, Jupiter, Saturn, these 5 planets were known to ancient sky watchers without any instrument at all. They moved against the fixed stars in ways that were visible, trackable, predictable enough that cultures across thousands of years built calendars and mythology and navigation systems around their patterns. They were simply there, in the night sky, available to anyone who looked up with patience and attention. Uranus changed that. William Herschel, a German-born musician who had settled in England and taught himself astronomy, observed Uranus through a telescope in March of 1781. He initially believed he had found a comet, something fuzzy and perhaps temporary, worth noting, but not immediately dramatic. It took additional observations over several weeks by Herschel and by other astronomers checking his work to confirm that the object showed a disk rather than a tail, moved too slowly for a comet, and followed an orbit that placed it far beyond Saturn. It was a planet, the first planet discovered in recorded history. The solar system, which had held 6 known members since ancient times, suddenly held 7. Herschel became famous. He named the planet Georgium Sidus, the Georgian star, after King George III, who rewarded him with a royal appointment. The astronomical community eventually settled on Uranus, following the tradition of naming planets for Greek and Roman deities, though Herschel never much liked that choice. For decades after its discovery, Uranus was studied carefully enough that astronomers began accumulating precise measurements of its position over time. And those measurements, as they accumulated, revealed something quietly troubling. The planet was not moving quite the way it should. Given the gravitation influence of every known body in the solar system, Uranus kept drifting slightly from the path the equations predicted. The drift was small, but it was real, and it was consistent. Something was pulling at Uranus from a direction the models had not accounted for. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, worked this problem independently and arrived at nearly the same answer. There was another planet out there, beyond Uranus, massive enough to cause the observed drift, in a position that could be calculated from the pattern of the disturbance. Both men produced predictions. Le Verrier shared his calculations with the Berlin Observatory in September of 1846. Johann Galle pointed a telescope at the coordinates that same night and found Neptune within 1 degree of where Le Verrier had said it would be. Neptune was not discovered by looking, it was discovered by reasoning. A planet announced by the behavior of another planet found where mathematics said it had to be. There is something worth resting in for a moment in that sequence. Ancient navigators looked up and named the wandering lights they saw. They built their knowledge from direct, patient observation across generations. And then, more than 2,000 years into that tradition of careful looking, a planet was found without looking at all, found by noticing the shape of an absence, the signature of something invisible pressing on something visible. The solar system had a new member before anyone had actually seen it, long before any spacecraft was designed, long before the concept of a space program existed. People working with nothing but mathematics and glass lenses had extended the known solar system by 2 entire planets in less than a century. Both discoveries came from a kind of attention that is different from the kind we usually mean when we talk about watching the sky. Not the attention of looking at something directly, the attention of noticing when something does not quite fit. That same quality of attention would later define everything we know and do not know about these two worlds. Before a single spacecraft was designed to visit the outer solar system, before the trajectory calculations were run, before any engineer sat down with the problem of how to send something across 3 billion kilometers and have it arrive at a precise location, years later, there was a peculiarity about Uranus that had been sitting in the data for decades without a fully satisfying explanation. Uranus is tilted. Every planet in the solar system rotates on an axis that is angled relative to the plane of its orbit around the Sun. Earth's axial tilt is about 23.5 degrees. Mars is close to that. Saturn is about 27 degrees. These tilts create seasons. The hemisphere that leans toward the Sun receives more light and warmth. Then the planet moves to the other side of its orbit, and that hemisphere leans away. Uranus has an axial tilt of about 98 degrees. That number sounds abstract until you think about what it means geometrically. A tilt of 90 degrees would mean the planet's axis lies perfectly in the plane of its orbit, pointing sideways rather than up. A tilt of 98 degrees means the axis is slightly past horizontal, tipped slightly beyond sideways, so that technically, the planet rotates in the opposite direction to most other planets when you account for the full geometry. The practical consequence of this is that Uranus does not experience seasons the way other planets do. It experiences something stranger. During part of its 84-year orbit around the Sun, one pole points almost directly at the Sun for decades at a time. The hemisphere facing the Sun receives continuous daylight for about 21 years. The hemisphere facing away sits in continuous darkness for the same period. Then the planet moves far enough around its orbit that the situation gradually reverses. During the Voyager 2 flyby in 1986, Uranus happened to be in a configuration where its south pole was pointed roughly toward the Sun. Voyager approached from that direction. What the spacecraft saw was a planet that appeared nearly featureless. From that angle, a pale blue-green disk with almost no visible cloud structure, no obvious storm systems, nothing like the dramatic bands and swirls of Jupiter or Saturn. Some scientists initially described it as the most boring planet in the solar system. That characterization turned out to be an artifact of when and from where Voyager looked, not a genuine property of the planet. Later observations from Earth, made during the 2000s and 2010s, as Uranus moved into a part of its orbit where its equatorial region faced the Sun, revealed a much more active atmosphere. Bright storm systems appeared. Cloud features became visible. The planet that had seemed almost inert during the Voyager flyby turned out to be a dynamic place. It had simply been showing its least active face at the only moment any spacecraft had ever visited. The tilt itself remains incompletely explained. The most widely accepted theory is that Uranus was struck by a large object, perhaps something roughly the mass of Earth during the early solar system, when collisions between planetary bodies were far more common than they are now. An impact of sufficient size and angle could have knocked the planet onto its side. The geometry of the tilt is consistent with this kind of event. The internal structure of Uranus is also slightly asymmetric in ways that might reflect such a collision. But no one has been able to confirm this directly. The evidence is circumstantial. The mathematics works. The scenario is plausible. It fits with what we know about the chaotic early solar system, and it remains, as of now, the best explanation, rather than a confirmed fact. Neptune's tilt, by contrast, is about 28 degrees closer to Earth's, more typical. But Neptune has its own strangeness. Its largest moon, Triton, orbits in the wrong direction. Every other large moon in the solar system orbits in the same direction its planet rotates. Triton orbits Neptune in the opposite direction, a retrograde orbit that is almost certainly not original. A moon that formed alongside Neptune in the same disk of material that built the planet would have orbited in the standard direction. Triton almost certainly did not form alongside Neptune. It was almost certainly captured, a wandering body from the outer solar system that came too close to Neptune at some point in the distant past and was pulled into orbit by the planet's gravity, rather than continuing on its previous path. Captured moons on retrograde orbits are gravitationally unstable over very long timescales. The tidal interaction between Neptune and Triton slowly drains energy from the moon's orbit, causing Triton to spiral gradually inward. In roughly 3.5 billion years, Triton will approach close enough that Neptune's tidal forces will tear it apart. The moon will break up, and the debris will spread into a ring system around Neptune, one that, by some estimates, may be more dramatic than Saturn's rings are today. Triton is currently, in a slow and invisible way, falling toward the planet it orbits. None of this was known before Voyager 2 arrived. The retrograde orbit had been detected from Earth, but the full significance of it, what it implied about Triton's origin and fate, came from the close observations the spacecraft made during its few days near Neptune in August 1989. Voyager 2 found that Triton's surface is covered with nitrogen ice. Temperatures there reach about -235 degrees Celsius, making it one of the coldest surfaces in the solar system. And yet, despite that cold, Voyager detected geysers. Not liquid geysers, not volcanic eruptions, but dark plumes of nitrogen gas venting from the surface, rising several kilometers before being swept sideways by Triton's thin atmosphere. The heat driving those plumes does not come from Triton's interior. It comes from the Sun. Solar radiation, even at Neptune's enormous distance, penetrates the translucent surface nitrogen ice and heats the dark material beneath it. The trapped heat converts subsurface nitrogen from solid to gas. The gas finds a crack and rises, geysers driven by sunlight, on the coldest large surface in the known solar system. That single observation from a spacecraft moving at high speed through the Neptune system, gathering data for a few hours, has shaped our understanding of Triton ever since. It is also one of the last close observations of that moon that any instrument has ever made. What Voyager 2 found inside these two planets, or rather, what it suggested about their interiors without being able to directly observe them, turned out to be one of the most consequential scientific legacies of those brief flybys. Both Uranus and Neptune are categorized as ice giants. That name requires some explanation, because neither planet is made primarily of ice in the way the word is commonly used. The ice in Ice Giant refers to something more technical compounds like water, methane, and ammonia that, under the extreme pressures found in the interiors of these worlds, exist in states that are neither the solid ice of a frozen lake nor the gas of an atmosphere. They exist as hot, dense, electrically conducting fluids, pressurized beyond anything achievable in a laboratory on Earth, behaving in ways that only become possible when millions of atmospheres of pressure compress matter into forms it does not ordinarily take. Below the visible cloud layers of both planets, the pressure climbs rapidly. The atmosphere transitions into something denser. Deeper still, conditions become extreme enough that water molecules are thought to break apart and recombine in unusual ways. Some models suggest that deep inside both worlds, carbon atoms squeezed under these pressures may precipitate out of the surrounding fluid and sink toward the core as crystalline structures, diamonds forming continuously, falling slowly through the interior toward the center of the planet. This idea, diamond rain inside Uranus and Neptune, is not confirmed. It cannot be confirmed with any instrument currently in existence, because no instrument has ever penetrated below the cloud tops of either world. It comes from laboratory experiments that recreate the pressure and temperature conditions expected at depth, from the behavior of carbon containing compounds under extreme compression, and from theoretical models of how those materials should behave. The experiments are real. The models are grounded in established physics. But the interiors of these planets remain, in direct observational terms, entirely unknown. What Voyager 2 did measure, and what remains one of the most genuinely puzzling results of either flyby, is the magnetic field structure of both worlds. Most planets with significant magnetic fields have fields that are roughly aligned with their rotation axis. Earth's magnetic field is tilted about 11 degrees from the geographic poles. Saturn's is nearly perfectly aligned. Jupiter's is tilted about 10 degrees. This makes intuitive sense in the most common model of how planetary magnetic fields are generated by the circulation of electrically conducting fluid in the planet's interior, driven by rotation. A rotating planet spinning around a roughly vertical axis tends to generate a magnetic field that points in roughly the same direction. Uranus's magnetic field is tilted about 60 degrees from its rotation axis. Neptune's is tilted about 47 degrees, and neither field is centered anywhere near the center of the planet. Uranus's magnetic field appears to originate from a point significantly offset from the planet's geometric center. Neptune's field is similarly off-center, generating a field so asymmetric that the strength varies dramatically across the planet's surface, depending on which side you are measuring from. These fields are strange. They do not fit the standard picture of how a planetary magnetic field is generated. Something about the interiors of these two worlds, the distribution of conducting material, the way heat moves through them, the depth at which the field-generating region sits, produces magnetic geometries unlike anything seen in the inner solar system. One possibility is that the conducting layer responsible for the field is not deep in the interior, as it is in Jupiter and Saturn, but sits in a shallower region where water and ammonia exist in a conducting fluid state. A conducting layer in a shallower, more irregular region of the planet could generate a more chaotic, off-axis field. But this is again a model, an attempt to explain something genuinely puzzling using physics that seems applicable, without the ability to go and look directly. There is a child somewhere tonight, or there was, in some generation past, who held a compass in their hands and watched the needle swing north without understanding why. The needle moved because of a field invisible to every human sense, generated deep inside the Earth by processes that took centuries of science to partially understand. Uranus and Neptune have their own invisible fields, stranger than Earth's, generated by processes that current science cannot fully account for. The compass needle would swing in unusual directions on those worlds, pointing not toward a simple pole, but toward something more complex, something that changes more dramatically as you move around the surface. Every grandmother who pointed upward at a bright planet near the horizon was pointing at an object whose interior was, in that moment, and every moment before and since, quietly doing something that no model has yet fully explained. The magnetic fields of Uranus and Neptune are not incidental details. They connect to the fundamental question of what these planets are made of inside, how their interiors are structured, and why two worlds that appear so similar from a distance behave so differently in ways the instruments can detect. Uranus, despite being closer to the Sun than Neptune, is actually colder at its cloud tops. Neptune, farther out, emits significantly more heat than it receives from the Sun, suggesting its interior is releasing stored energy from its formation, still slowly cooling after 4.5 billion years. Uranus emits almost no excess heat at all. Its interior appears, from the outside, to be releasing almost nothing. Why planets of similar size and composition would behave so differently in this regard is not understood. The Voyager data raised the question clearly. Nothing since has answered it. These are not small puzzles. They are questions about how planetary interiors work, how magnetic fields form, how heat moves through dense compressed matter questions, with implications that extend beyond Uranus and Neptune to the hundreds of ice giant planets now known to orbit other stars. Because it turns out that ice giants, as a class, are among the most common planetary types in the galaxy. We happen to have 2 of them in our own solar system, close enough in principle to visit, and we have visited them once, briefly, more than 3 decades ago, with a spacecraft that was not specifically designed for either of them. When Voyager 2 left Neptune behind in August of 1989, it carried no more planetary destinations. It had completed the Grand Tour, a trajectory made possible by a rare alignment of the outer planets that occurs roughly once every 175 years, allowing a single spacecraft to swing from Jupiter to Saturn to Uranus to Neptune, using each planet's gravity to accelerate toward the next. The alignment that made this possible would not occur again within any planned spacecraft's operational lifetime. Voyager 2 continued outward. It is still traveling, but it was not going back. In the years and decades that followed, the scientific community turned to other priorities. Mars attracted enormous attention and resources. The discovery of subsurface water on Europa revived interest in Jupiter's moons. Saturn's system became the focus of the Cassini mission, which spent 13 years in orbit and transformed our understanding of Saturn, its rings, Triton, and Enceladus. The inner solar system, Mars, and the gas giants absorbed the major planetary science missions of the 1990s, 2000s, and 2010s. Uranus and Neptune received no dedicated spacecraft, no orbiter, no probe, nothing. Astronomers continued observing both planets from Earth and from space telescopes not specifically designed for planetary work. The Hubble Space Telescope accumulated observations of both worlds over decades, tracking seasonal changes in Uranus's atmosphere as the planet moved through its long orbital cycle, watching storm systems develop and fade on Neptune. The data helped. It refined models and filled in some gaps. But a telescope observing from Earth's orbit, even the most capable one in existence, sees Uranus and Neptune as small disks a few arcseconds across at best, rather than as the detailed, three-dimensional worlds that a nearby spacecraft would reveal. The gap between what can be learned from a distance and what can be learned up close is not a small one. Consider what the Cassini mission revealed about Saturn that could not have been discovered from Earth. The detailed structure of the ring system, the gaps, the waves, the embedded moonlets, the way different ring regions behave differently. The geysers of Enceladus, which were not known to exist before Cassini flew through the plume and tasted the material being ejected. The lakes and rivers of liquid methane on Titan's surface, mapped by radar because the moon's thick atmosphere blocks optical observation. The complex chemistry of Saturn's upper atmosphere. None of this was accessible from Earth. It required proximity. It required years of sustained observation from an orbiting platform. Uranus and Neptune have no Cassini. They have Voyager 2's few hours of data, and everything that telescopes can see from several billion kilometers away. the scientific community has not been unaware of this gap. Throughout the 2000s and 2010s, mission concept teams produced detailed proposals for ice giant orbiters spacecraft that could travel to Uranus or Neptune, enter orbit, and spend years studying the planet the way Cassini studied Saturn. Each of these proposals went through rounds of review, refinement, and ultimately deferral as other priorities competed for limited funding. In 2022, the National Academies of Sciences released its Planetary Science and Astrobiology Decadal Survey, the document that sets the priority order for NASA's planetary science program for the following decade. The survey, which represents the consensus of the planetary science community after years of study and deliberation, named an Uranus orbiter and probe as the top priority flagship mission for the coming decade, above Europa Clipper's follow-on work, above any Mars mission, above any return to the outer solar system's other destinations. Uranus, the planet that had been waiting since 1986. The reasoning was straightforward and had been building for years. Ice giants are the most common planetary type in the galaxy. Thousands of exoplanets detected around other stars fall into the size range between Earth and Neptune, too large to be rocky worlds, too small to be gas giants. Understanding how Uranus and Neptune formed, what their interiors contain, why their magnetic fields behave as they do, and what drives their atmospheric dynamics would directly inform the interpretation of those distant worlds. Every ice giant planet detected around another star is, in some sense, a planet we are trying to understand with tools calibrated for gas giants and rocky worlds, because ice giants are the type we know least about. There is a quiet irony in that. The two planets in our own solar system that we have visited least, that we understand most poorly, that generate the most unresolved scientific questions, happen to represent the planetary category most commonly found elsewhere in the galaxy. The universe, it turns out, makes ice giants readily. We just have not spent much time with our own. The Decadal Survey's recommendation did not immediately produce a mission. The path from a priority recommendation to an approved, funded, designed, built, launched, and operational spacecraft typically takes 15 to 20 years. An Uranus orbiter recommended in 2022 would, under the most optimistic, realistic timeline, not arrive at Uranus until sometime in the 2040s. The trajectory options that minimize travel time and fuel requirements are limited by orbital mechanics, and several favorable launch windows in the late 2020s and early 2030s are already beginning to narrow. This is the position the science stands in tonight. Two planets, each holding major unresolved questions. One spacecraft flyby each more than 35 years ago. A recommendation, now several years old, that both represents genuine scientific urgency and faces the ordinary long patience that all spacecraft missions require. Instruments that can observe from a distance but cannot answer the deep questions, and a clock running quietly, marking the slow passage of time in which the best launch opportunities are counted not in months, but in years. Right now, as you are resting, the instruments on Earth's largest telescopes are accumulating photons that traveled from Uranus and Neptune for hours before reaching the mirrors pointed at them. Astronomers are processing those observations, fitting them to models, trying to extract the most from what can be seen from here. They are doing careful, patient work, and they are aware that what they need most is something that is not yet on the way. Neptune has a storm. It has had several, observed at different points over the decades since Voyager 2 passed through. The most famous was the Great Dark Spot, a storm system roughly the size of Earth, that Voyager photographed in 1989, a vast counterclockwise rotation in Neptune's southern hemisphere, visually reminiscent of Jupiter's Great Red Spot. When Hubble looked at Neptune a few years after Voyager's visit, the Great Dark Spot was gone. A new dark spot had appeared in the northern hemisphere. That one also eventually faded. Others have been observed since, appearing and disappearing on timescales of years, each one a weather system larger than an entire planet, each one temporary. The winds that surround and drive these storms are the fastest measured on any planet in the solar system. Near Neptune's equator, wind speeds reach roughly 2,000 kilometers per hour, supersonic relative to Earth's atmosphere, sustained continuously around a planet with no solid surface to slow them, no friction from land or ocean to drain their energy. The source of the energy driving those winds is not fully understood. Neptune receives very little heat from the Sun at its distance, yet its atmosphere is far more dynamic than Uranus's, which sits closer to the Sun but shows less activity. The internal heat Neptune releases, the slow cooling of its formation energy, appears to drive much of the atmospheric circulation in ways that Uranus, releasing almost no comparable internal heat, cannot. Why these two similar worlds diverge so sharply in their atmospheric behavior remains one of the cleaner unsolved questions about the outer solar system. The answer almost certainly lies in their interiors, in whatever structural difference caused Uranus to retain its internal heat so effectively that almost none escapes, while Neptune continues releasing it. But the interiors, as always, are inaccessible. Uranus's atmosphere, for its part, is not entirely quiet. The storms observed from Hubble and from ground-based telescopes in the 2000s and 2010s showed that the planet has genuine weather-bright cloud features, convective systems, localized storms that develop and dissipate. Some of these were bright enough to be detected from Earth with large amateur telescopes, once observers knew where to look. One particularly bright storm system appeared in Uranus's northern hemisphere around 2014, as that hemisphere entered its long summer after decades of polar winter. It generated significant attention because it demonstrated clearly that Uranus's seemingly featureless appearance during the Voyager flyby had been a seasonal artifact. The planet had been sleeping, in a sense, or at least showing the quiet face of its polar winter. As sunlight returned to the northern latitudes over subsequent years, the atmosphere woke up. The ring systems of both planets add another layer to the picture. Uranus has 13 known rings, discovered in 1977, when the planet passed in front of a distant star, and astronomers watching the star's light noticed it flickering before and after. The planet itself blocked the rings intercepting the starlight symmetrically on both sides of the disk. The rings are narrow, dark, and physically different from Saturn's broad, bright, icy ring system. Uranus's rings appear to be composed of dark material, possibly organic compounds, possibly material coated with radiation-processed carbon that reflects very little light. They are difficult to observe, even with powerful telescopes, which is why their existence was not suspected until that 1977 occultation observation revealed them by accident. Neptune has 5 named rings, also narrow and dark, also discovered through occultation observations before Voyager confirmed and detailed them. Neptune's rings have an unusual property: they are clumpy. Rather than being evenly distributed around the planet's circumference, the material in some of Neptune's rings is concentrated into denser arcs, with gaps between them. This clumpiness should not persist over long timescales, without some mechanism maintaining it. Small moons embedded in or near the rings are thought to gravitationally confine the material, preventing it from spreading. But the details of exactly how this works remain imprecisely understood. Both ring systems are far younger than the planets themselves, almost certainly. Material in planetary rings does not persist indefinitely. Collisions between ring particles grind them smaller over time. Radiation pressure pushes fine particles away, and gravitational interactions with nearby moons constantly perturb the system. Saturn's rings, long assumed to be ancient, have been estimated by Cassini data to be only a few 100 million years old, a fraction of the solar system's age. The rings of Uranus and Neptune are similarly thought to be geologically young, the products of relatively recent collisions or tidal disruptions of small moons, rather than remnants of the material that built the planets. The moon systems of both planets are not small families. Uranus has 27 known moons, all named after characters from Shakespeare and Alexander Pope. The 5 largest: Miranda, Ariel, Umbriel, Titania, and Oberon range in size from about 500 to more than 1,500 kilometers across. Miranda, the smallest of the 5 major moons, is perhaps the most visually striking object Voyager 2 photographed in the entire Uranian system. Its surface is a geological patchwork, ancient cratered terrain interrupted by enormous canyons, chevron-shaped ridges, and cliffs that in some regions drop nearly 20 kilometers from top to bottom. Verona Rupes, one of Miranda's escarpments, is the tallest known cliff in the solar system. How Miranda came to look the way it does is not fully resolved. One early hypothesis suggested the moon had been shattered by a large impact and reassembled itself under gravity, producing the chaotic surface texture. Current thinking leans toward geological processes, tidal heating, during a past period of orbital resonance with other moons driving internal activity that deformed the surface in unusual ways. But Miranda has received almost no observational attention since the Voyager flyby, and its surface remains, in detailed terms, essentially unknown. Neptune has 14 known moons. Triton, the largest, accounts for more than 99% of the total mass orbiting Neptune, an extraordinary concentration that reflects how dominant Triton is in that system. The remaining moons are small, irregularly shaped, and mostly discovered from Earth-based observations or from reanalysis of Voyager imaging data. Several were found only in the 2000s and 2010s, hiding in archival images or revealed by more sensitive ground-based surveys. What none of these observations have been able to determine is whether any of the larger moons of Uranus or Neptune harbor liquid water beneath their surfaces. The discovery of subsurface oceans on Europa, Enceladus, and Ganymede reshaped how planetary scientists think about habitability in the outer solar system. The conditions that allow liquid water to persist beneath an icy surface, tidal heating, sufficient insulating ice, the right chemical environment are not unique to the Jupiter and Saturn systems. Several of Uranus's larger moons show surface features suggesting past geological activity. Ariel and Titania both have canyon systems that may indicate tectonic processes, possibly driven by past tidal heating. Miranda's deformed terrain points toward internal activity. Whether any of these worlds retain liquid water today in hidden oceans beneath their ice shells is genuinely unknown. Not unknown in the sense of slightly uncertain. Unknown in the sense that no instrument currently measuring anything about these moons can answer the question. An orbiter equipped with an ice-penetrating radar, a magnetometer sensitive enough to detect the inductive signature of a subsurface conductor, and instruments to analyze any material escaping from the surface. The kind of instrument suite that Europa Clipper carries to Jupiter could begin to answer whether any of Uranus's moons are ocean worlds. Without such a mission, the question remains in the same state. It was in the morning after Voyager 2 made its flyby and continued on its way. The moons wait, the data waits, the question waits. It has been waiting for a long time in the quiet of the outer solar system, far from the instruments that could answer it. There is a particular kind of scientific patience that does not get discussed much outside the communities that practice it. It is not the patience of waiting for an experiment to finish, or for a paper to clear review, or for a grant application to receive a decision. Those waits are measured in months, occasionally in years. The patience required for outer solar system science is measured differently. It is measured in the careers of researchers who will spend their entire working lives contributing to a mission they may not see complete. It is measured in the retirements of scientists who advocated for a mission in their 30s and will be in their 70s or beyond before the spacecraft arrives at its destination. It is measured against the slow arc of institutional memory, which must carry the rationale and the accumulated knowledge of a project across decades and personnel changes and shifting budget environments. The Cassini mission to Saturn was proposed in the 1980s. It launched in 1997. It arrived at Saturn in 2004. It ended in 2017. The scientists who made its earliest discoveries at Saturn were not, in most cases, the ones who first proposed the mission. The ones who proposed it were often retired. or had moved to other work, or in some cases had died, by the time the spacecraft was producing its most significant results. This is the normal timescale of outer solar system exploration. A mission to Uranus, if approved and funded in the next few years, would likely launch sometime in the late 2020s or early 2030s to take advantage of favorable trajectory options. The journey to Uranus, depending on the trajectory, takes roughly 13 years. Arrival would come in the early 2040s. A primary mission of several years in orbit would then produce its most significant results in the mid to late 2040s. Graduate students entering planetary science programs today, students who may be in their mid-20s now, would be in their 40s or early 50s before the first data from an Uranus orbiter reached Earth. That is not an argument against the mission. It is an argument for beginning it. The scientists who have spent the past 2 decades studying Uranus and Neptune from a distance, with instruments not designed for the task, working with data more than 3 decades old as their primary close-up reference, are not working from a place of discouragement. The scientific questions are too interesting for discouragement. The clarity about what is not known and about what a properly equipped orbiter could determine is too precise. The community that produced the decadal survey recommendation did so from a position of genuine scientific excitement about what an ice giant mission would find, not just for understanding Uranus and Neptune specifically, but for what those findings would mean for the interpretation of hundreds of ice giant planets now known around other stars. The telescope that found many of those exoplanets, the Kepler Space Telescope, operating from 2009 to 2018, surveyed more than 500,000 stars and confirmed thousands of planetary systems. Among its most consistent findings was that planets in the size range between Earth and Neptune, sometimes called sub-Neptunes or mini-Neptunes, are extraordinarily common. They appear around a substantial fraction of Sun-like stars. They are, statistically, the most common type of planet in the galaxy, and they are the type we understand least well. Part of the difficulty is that sub-Neptunes and Neptune-sized planets span a range of possible compositions. Some may be rocky worlds with thick, hydrogen-rich atmospheres. Some may be true ice giants, fluid interiors of compressed water, methane, and ammonia beneath gaseous envelopes. Some may be something in between, or something else entirely. Distinguishing between these possibilities from the light of a distant star requires knowing what each type of planet actually looks like. Up close, its atmospheric composition, its thermal emission, its magnetic signature. Models built on close observations of Uranus and Neptune would make those distant exoplanet observations far more interpretable. In other words, the scientific value of understanding our own ice giants extends across the galaxy. Knowing what Uranus actually contains in its interior, how its magnetic field is generated, why it releases so little internal heat, and how its atmospheric chemistry works, would provide a calibration point for interpreting ice giant planets around other stars in ways that no amount of additional telescope time on those distant worlds can substitute for. The nearest ice giants are in our own solar system, accessible in principle, orbited by nothing, observed up close one waiting. There is a quality to scientific waiting that is different from ordinary waiting. Ordinary waiting is passive time passing while nothing changes. Scientific waiting accumulates. The instruments improve. The models sharpen. Each year of telescope observation of Uranus and Neptune adds to the dataset, refines the predictions, narrows the questions. When an orbiter finally arrives, if and when one does, it will arrive at a target that has been studied far more carefully than Voyager 2's designers could have imagined possible. The encounter will not begin with the blank slate that the 1986 and 1989 flybys faced. It will begin with decades of accumulated questions precise enough to design specific instruments and specific observations around. The waiting in that sense, it is preparatory. Ancient civilizations in the Mediterranean and the Middle East tracked the movements of the outer planets across the sky with patient attention that accumulated across generations, not because they understood what those objects were, but because the patterns mattered. Sailors navigated by star positions that had been catalogued and refined over centuries. The knowledge that guided a ship in the 2nd century had been built on observations made in the 4th century before that. The instruments changed across those generations. The care with which the data was gathered and preserved did not. The scientific communities building models of ice giant interiors today, refining trajectory options, designing instrument suites for a mission not yet approved, are doing something recognizable in that longer frame. The tools are entirely different. The scale of what is known and not known is entirely different. But the quality of attention patient, cumulative, handed across generations of researchers, is continuous with something very old. The data from a Uranus orbiter, when it eventually arrives, will be analyzed by people who have not yet decided to become scientists. There is one more thing Voyager 2 did at Neptune that has not been fully appreciated in the decades since. As the spacecraft completed its flyby and began its long departure from the solar system, mission controllers used the encounter to perform a final gravity, a sister swing around Neptune that bent Voyager 2's trajectory southward, away from the plane in which most of the solar system's planets orbit. This was a deliberate choice. With Neptune as the last planetary destination, the trajectory that had been optimized for the Grand Tour naturally carried the spacecraft toward interstellar space. The Neptune encounter was shaped to send Voyager 2 out of the solar system in a direction different from Voyager 1, allowing the two spacecraft to sample different regions of the heliosphere as they departed. This means that humanity has now had two spacecraft pass through the outer boundary of the Sun's influence, the heliopause, where the solar wind gives way to the interstellar medium in different directions at different times. Voyager 1 crossed it in 2012. Voyager 2 crossed it in 2018. The measurements the two spacecraft made in those respective crossing regions were not identical, suggesting that the boundary of the heliosphere is not uniform, that it has structure, varying thickness, different properties in different directions. This was not known before those crossings happened. It could not have been known. And it was made possible in part by the trajectory that the Neptune flyby enabled. Voyager 2 is the only spacecraft ever to have visited 4 planets beyond the asteroid belt. Its trajectory through the outer solar system, shaped by the Grand Tour alignment and the gravity of each successive planet, is not something that can be replicated by pointing a new spacecraft in the same direction and launching it. The alignment that made the Grand Tour possible is gone. Future missions to the outer planets will take different paths, with different travel times, designed for different scientific goals. The trajectory Voyager 2 flew was, in a meaningful sense, unique to its moment in time. The data it gathered at Uranus and Neptune was gathered under similarly unrepeatable conditions. Not because the planets themselves have changed, or because another spacecraft could not visit them, but because Voyager 2 arrived at a specific moment in each planet's seasonal cycle, at a specific geometry, with instruments calibrated for specific measurements, and recorded what those specific conditions showed. Uranus in January 1986, with its south pole facing the Sun, presenting a nearly featureless atmosphere, with its magnetic field oriented in the particular direction it occupied at that moment. Neptune in August 1989, with Triton's geysers active, with the great dark spot present in the southern hemisphere, with a particular set of moons visible from the spacecraft's approach angle. Those conditions will not recur in the same combination. They are historical data in the fullest sense, not just data gathered in the past, but data that recorded a unique moment. Future missions will encounter different versions of these planets in different seasonal configurations, with different storm systems, with Triton at a different point in its long inward spiral. They will bring better instruments, more capable software, more precise trajectory control. They will be able to observe things Voyager 2 could not. They will also be observing worlds that have continued to evolve in the decades between encounters, in ways that the comparison between Voyager data and new data will make visible. This is how planetary science actually accumulates, not by replacing old data with new, but by building layers of observation across time, each layer illuminating something about how the planet or moon changes, or does not change, or changes in unexpected ways. The 35-year gap between Voyager and whatever comes next is scientifically painful. It is also, in retrospect, a long baseline long enough that seasonal changes, long-period atmospheric cycles, and the slow drift of Triton toward Neptune will all be measurable in the comparison. The gap is not only a loss, it is also data. Neptune has moved roughly a quarter of the way around its orbit since Voyager flew past it. Uranus has moved somewhat more than a third of the way around its own 84-year orbit. These are planets on long cycles, and the science of the coming decades will be able to observe them at phases of those cycles that Voyager never saw. Right now, the James Webb Space Telescope has begun collecting observations of both worlds, its infrared sensitivity and its position in space far enough from Earth to avoid the distortions of the atmosphere. Give it capabilities that ground-based observatories cannot match. Early Webb observations of Neptune released in 2022 showed the planet's ring system more clearly than any previous telescope had captured it. From Earth's vicinity, thin, dark arcs surrounding a blue-gray planet, Triton visible as a bright point nearby. Webb observations of Uranus have revealed new detail in its ring structure and atmospheric features. These are telescope observations. They are not the same as an orbiter. They cannot measure the magnetic field, analyze the atmosphere's chemistry below the cloud tops, study the surfaces of the moons, or detect the inductive signatures of subsurface oceans. But they extend the continuous baseline of observation, add new information to the models, and keep scientific attention on these worlds during the long interval before a dedicated mission arrives. The people at the James Webb Space Telescope Science Institute who planned and executed those observations, who processed the data, who are now interpreting what the images and spectra contain, they are contributing to the same ongoing conversation that Voyager 2's cameras began in 1986 and 1989. Across the different instruments, the different facilities, the different decades, the scientific attention on these two worlds has not fully stopped. It has continued imperfect and incomplete, doing what can be done with the tools available. That kind of continuity imperfect, maintained across institutional and generational change, working always at the edge of what the current instruments allow, is what keeps a scientific question alive until the tools needed to answer it finally arrive. The tools are improving. The question is the same one it has been since Voyager 2 crossed into interstellar space and left these two worlds behind. What are they really on the inside? Somewhere in the outer solar system tonight, two worlds are turning in the dark. Uranus completes a rotation every 17 hours or so faster than Earth, though from a distance its extreme tilt makes the rotation difficult to visualize in ordinary terms. Neptune rotates in about 16 hours. Both planets are moving through their long orbits, Uranus taking 84 years to circle the Sun, Neptune taking 165. Neptune completed its first full orbit since its discovery, only in 2011 the first time, since Johann Galle found it in the telescope that September night in 1846, that it had returned to the same position in the sky where it was first seen. One orbit. In the entire history of Neptune's discovery and study by human beings, the planet has gone around the Sun once. That number does something to the sense of time, if you let it. The civilizations that built the first telescopes capable of finding Neptune did not exist when Neptune was last in the position it occupied at its discovery. The scientific tradition that produced Leverrier's mathematical prediction was centuries in the making. The technology that allowed Galle to confirm it on the same night he received the coordinates was the product of generations of optical craftsmen. And in all the time since all the decades of observation, all the telescopes, all the theoretical work, all the Voyager data, all the Hubble images, all the Webb observations, Neptune has moved once around the Sun. Uranus has completed roughly 2.5 orbits since Herschel found it in 1781. The mathematics of that fact quietly expand into something large if you stay with it. 2.5 journeys around the Sun, each journey 84 years. The planet was there before the Industrial Revolution, before the first photograph was taken, before the first telegraph message was sent, before the discovery of Neptune itself, before the existence of the discipline called planetary science. It was there, turning on its tilted axis, its rings in place, its moons orbiting, its strange magnetic field threading through its interior, generating the field lines that no instrument would measure for another 2 centuries. It did not need to be understood to continue. The light that falls on Uranus's cloud tops tonight has been traveling for about 2 hours and 40 minutes since it left the Sun. By the time it arrives, it is faint enough that the planet sits in a kind of perpetual deep dusk bright by the standards of interstellar space, dim by the standards of any inner solar system afternoon. The atmosphere absorbs some of that light at specific wavelengths and reflects the rest. The particular wavelengths of methane absorption give Uranus its blue-green color. The light bounces back into space, travels for another 2.5 hours, and eventually some small fraction of it reaches a telescope on Earth or in Earth's orbit, where it is focused and measured and added to a growing data set. Neptune's reflected light takes about 4 hours to make the same journey back. Both streams of reflected sunlight are arriving continuously. They arrive whether or not any instrument is pointed in the right direction to receive them. They have been arriving since before the telescopes that could detect them existed. They will continue arriving after every telescope currently operating has been decommissioned. The question of what lies beneath those reflected surfaces, what the interiors contain, whether the moons hold water, how the magnetic fields are generated, why one planet runs cold and the other warm, that question travels with the light, in a sense. It has been present in every photon that reached a measuring instrument since Herschel first noticed an unusual disk in 1781. The light carried the question before anyone had thought to ask it. There is something in that worth resting beside, not the vastness of it, exactly, or the cold. Something quieter, the fact that the universe does not withhold its information. It sends the light regardless of whether we have built the instruments to read what the light contains. The ice giants have been transmitting in the only way a planet can, for as long as they have existed. The capacity to receive what they are sending has been building slowly, imperfectly, across centuries of instrument making and scientific patience. The next chapter of that reception is being designed somewhere right now, on a computer in a laboratory, in a spreadsheet of trajectory calculations, in the careful specification of a scientific instrument that needs to fit within a mass budget and survive a decade of interplanetary travel before it does its work. The people doing that designing are thinking about Uranus and Neptune with a precision that William Herschel would not have recognized as the same activity as pointing his handmade telescope at a curious disk in 1781. And yet it is. The same outward attention extended by every tool the intervening centuries made possible. What those designers want to know is what is inside, what the magnetic field is telling them about the interior structure, whether any of the moons hold oceans, why Uranus holds its heat and Neptune releases its own, whether the conditions deep inside either planet produce the forms of matter that laboratory experiments suggest are possible, but that no observation has ever confirmed. They want to go and look. The wanting has been building for a long time, and the answer requires proximity, an orbiter, patient years in the system, instruments designed for the specific questions these planets hold. Until that arrives, the work continues with the tools available. The data accumulates, the models sharpen. The gap between Voyager's brief visits and whatever comes next grows 1 year longer with each year that passes, and also 1 year more complete in its long baseline value. Both worlds will be where the calculations say they will be when a spacecraft finally arrives. The orbital mechanics are precise enough that the navigation will work, as it worked for Voyager, as it worked for Leverrier's prediction, as it has worked at every stage of outer solar system exploration. The planets are not going anywhere. They will be there. The southern sky holds different stars than the ones you can see from here. Centaurus, where Alpha Centauri burns, is a southern constellation. So is the small constellation Musca. And somewhere in the larger celestial coordinate system that contains all of it, Uranus and Neptune move along their long arcs, visible only as pale disks through any instrument trained on them from Earth, carrying their unresolved questions in the only way objects carry questions, by continuing to exist, unchanged in their essentials, patient across spans of time that dwarf any human concern. Tonight, 2 instruments on Earth are pointed at one or the other of them. Or perhaps none are. Perhaps the light arrives tonight without any telescope to meet it. It arrives, regardless. The dark holds both worlds, steady and unhurried. The light keeps crossing,